So it's amazing, it's exciting, it's frightening. At the same time, he sent me a check signed by him, the check for $2.56, which I can cash if I want.
LLMs will never take away your ability of thinking about complexity theory in the bus or in the car.
That one paper in Bioinformatics accumulated something like 30 times more citations than all the other 50 papers altogether. This classification of researchers called birds, who actually fly among all areas and observe everything. And there are researchers called frogs who actually stay in some small and tiny area and try to dig.
A researcher asked an AI, can you prove that P equals NP? AI replied, of course, I just need an exponential time to explain it. The researcher said, that's not very helpful. AI answered, hey, if you wanted polynomial time answers, you shouldn't have trained me on internet comments.
So first of all, I'm really pleased that we're going to have the conversation that we're going to have right now. I'm glad to present you, our dear listeners, Alexander Kulikov, who is the great math educator, just a wonderful person, complexity theorist who studies the limits of computation, and also the creator of tools that win different competitions. So for us as researchers in JetBrains research, all of that, different types of research, creating tools and education are, well, really important and interesting topics. We are today here at JetBrains Research Podcast. I'm Ilya Zakharov. With me today is Igor Slinko. And we're going to talk with our colleague, Alexander. It's not my first talk with Alexander, and it's always a pleasure for me. And I hope we will be able to share this pleasure with others. So, nice to meet you. Nice to meet you, Alexander. Nice to meet you, Igor. How are you today?
Good. Hi, everybody. Hi, Igor and Ilya. How are you?
So you've just returned from some conference. Where have you been? What did you do? What interesting thing have you learned?
Yeah, I've been to the conference called STACS. I'm not sure that at this point okay. So this is a conference on theoretical computer science. Together with our student Nikolai Chukin, who is also currently an intern at JetBrains. We were presenting 2 papers. We attended many talks, actually met some new people, met some old friends. Also, hopefully we will be able to start some new research projects with some of these colleagues. So as usual, so this was great. I mean, STACS is one of the greatest European, so to say, conferences on theoretical computer science. There are also 3 top conferences in our field in the US, namely STOCK, FOX, and SODA. So also on my way to France, I went through Switzerland, where again I met some of my old friends. So this was a pleasure.
So you've just been to one of the conferences, big conferences in the field, and from what I can imagine from afar, the field of theoretical computer science is in a very, very strange, or maybe, I don't know, at least very interesting position when AI is already winning some competitions like IMO medal. At the same time, there are some problems, real scientific problems that are being solved by AI. By the time we're talking, maybe the biggest thing that happened, was it last week, was this short commentary from Donald Knuth that he solved one of his real world problems with AI. How do you feel about all that? Well, how does it feel to be in this field when everything is changing so fast?
Well, it's hard to tell. So it's amazing. It's exciting. It's frightening at the same time. I'm also, it was just cool to read how Don Knuth, who is like a living legend, how he phrases it. So he starts his short note on this with shock, And indeed, it is just interesting how it was Claude, right, that solved one of his problems. How it was interesting just to read the thought process about this. So in theoretical computer science, I would say that currently we don't have too many new interesting results proved with the help of AI, but we'll see. I mean, definitely there are some. Unfortunately, I personally was not able to get any new interesting results with the help of AI. I try a lot. So I was mainly discussing my research problems with chatbots, and they definitely become smarter and smarter. So it is interesting to discuss with them. But we'll see. Probably they will help me someday. My current plan is also to start writing some software that can produce some new results with the help of AI agents. I've seen also some reports by mathematicians and computer scientists that they got some new interesting results with the help of AI. So definitely there will be more and more such results. The question is whether AI will be able to solve some of our main open problems, so to say. For example, the problem of P versus NP, which is the open problem in theoretical computer science, and probably even in computer science, and probably one of the main problems in mathematics. We'll see. But I'm excited once again, and I'm a little bit frightened, I must admit.
Well, as most of us are. I mean, it's frightening to be in such fastly changing environment. But I think we'll be able to come back to that. Before, let's maybe talk a little bit about yourself. So you are a complexity theorist. You
Right.
lead a lab about it. You do quite a lot of education, and at the same time, you are a colleague in JetBrains, a company that makes IDE. For those of you who might not know that, what is your role inside JetBrains? How does it work for you to be on the verge of theoretical computer science, working in industry? How does it work? What's your, I don't know, day job? What are your priorities? How do you orient yourself between these two different worlds?
Right. So I guess my main role in JetBrains is not the head of this algorithms and complexity laboratory, but probably the head of the Bachelor program where I teach, and I'm responsible for this program. So we try to think a lot about the curriculum, the contents of our courses. We discuss how to adjust the program to what is happening in the world, in the whole world, and in the world of programming and development in particular. So probably my main responsibility in JetBrains is to organize this Bachelor program. And I would say that my second responsibility is to do this fundamental research. I must admit that this research has almost nothing to do with JetBrains tools. So I'm working on problems that do not have a direct impact on the products of JetBrains. And even if I prove some of my dream theorems, I mean, it would not help JetBrains to improve their products or to sell them better or whatever. Still, I mean, it is important to also work on some fundamental problems, of course.
Agree. Cannot agree more. I mean, we're doing a lot of different fundamental research in our department as well. What caught my mind, you were saying, and this is maybe, for me, maybe the most important topic, not only for this particular talk, but in general these days, is this really environment that changes so fast. And you are saying that for a bachelor program, you're always trying to understand what should be in this program, how to adjust it to what's happening in the world. Can you maybe give us a high-level overview of that? How often do you change topics? What do you think is becoming important these days? What is classic and will still be classic, I don't know, 50 years from now. So how do you orient in this space that is evolving?
Yeah, so I must admit that it is still not clear to me what is going to be what is still going to be important, not even in 50 years, but even in 1 year. I would say. I mean, I'm not sure that I envision how people are going to write code in 1 year, because it is changing so rapidly that once again, I'm just a bit nervous about this. So we have a weekly meeting with all other professors in our bachelor program. So we are trying to ensure that together with our students, we at least try some of the modern tools. On the other hand, it's always been a case for us that we are not interested in teaching tools. So we must, of course, focus on some fundamentals, but even in terms of fundamentals, it is not so clear what is the right amount of fundamentals for future specialists, for future, I don't know, software developers or just engineers. So we do believe that mathematics is still important, of course. I mean, the question is, what is the right amount of mathematics? I still believe that our main goal in our bachelor program is to help students to be able to learn complex things quickly, and I hope that it will still be usable in their future careers. And at every point of time, we just try to ensure that our professors are teaching something which is sufficiently complex. So we are not learning tools, and we're not teaching tools. We're not teaching just syntax of programming languages, but we are teaching some fundamentals once again. But the devil is in the details, probably. So what is the right amount of mathematics? What exactly do we call fundamentals? What are mathematical fundamentals? What are computer science fundamentals, programming fundamentals?
What is sufficiently complex?
Exactly. So these are all open questions. I was trying to understand whether the curriculum of some top universities actually changes. So we have our graduates or some colleagues who work or who study at MIT, at EPFL, and from what I learned, that the curriculum stays more or less the same. So some of the courses are adjusted a little bit. Some of the professors actually state on their web pages that they ask students not to use AI sometimes for solving homework. Sometimes they encourage them to use AI for some of the projects. At MIT, there are some additional courses or hackathons and AI clubs or stuff like this. So in particular, I guess, because when it comes to modern tools, to AI agents, then there are no professionals, no professors specializing especially in such fields. So there are no books. So the way probably to teach this and to learn this is to organize some different format of courses where professors probably try new tools together with students.
But hasn't this always been, at least at some point, the case for computer science education? I mean, it's evolving much faster than, technologies even before AI were evolving faster than books were written. What is similar in your experience? You've been doing that a lot, and what is really different? I believe there were a lot of professionals from the field before who are also presenting knowledge, from their personal experience without so many books about that.
Right. So I guess what is similar to, say, 10 years old, for example, is that universities are much slower than the industry. For example, this has always been the case. And one example is that, for example, if almost nobody uses Pascal as programming language in practice, it is still probably okay to use it for teaching some like first programming course, for example. And it was the case, probably 10 years ago. It's at some places, at high schools, for example. Then at some point, the universities finally realized that Pascal is not used anymore, and they switched to something, to Python, for example. What is different right now is that I think the pace of advancement is so high that it is not only challenging for universities to catch up, but it is also challenging for professionals to catch up. So what do we expect from universities at this point? At universities, there is also some bureaucracy, unfortunately, because it is usually not so easy to adjust the curriculum. In some cases, you first need to submit some proposal. Then this proposal is reviewed by some committee. Not just because of bureaucracy, but because this is done just to ensure that universities teach the material that they promise students to teach. For example, that they do not change the curriculum on the fly, but in our real world, in computer science, it is just too important to change it on the fly. So you're right. I agree that there are some similarities, and universities have always been slow, but something is fundamentally different at this point, because this pace of advancement, I think it is the first time that I see it in my life.
Cannot agree more. But I want to come back a little bit to the thing you've said, that you try to teach how to solve complex problems. And, it's hard to understand what are those, but do you have any examples? What kind of problems you believe are like very specific things are worth studying these days? And so this is the first question. And the second question, is there any research part on that? So there are some old classic problems that are worth studying. Do you also teach how to research? Do you have some joint research on complex mathematical things with the students?
So let me just admit it. So I have no idea how the world of computer science or the world of software engineering is going to look like in 4 years. Okay, so and at the same time, I am responsible for this computer science curriculum, which puts me into a strange position, unfortunately. So the best I can do is actually the same as what I did probably in computer science, in shaping like the computer science curriculum probably 10 or 15 years ago, which is strange because I just mentioned that the pace of development of the field right now is much higher. So what I believe our goal with our talented students is the following: we are trying to teach them during the 4 years to be able to solve complex tasks, right, and to be able to quickly catch up with complex things. We don't know which complex things exactly they will need to catch up in 4 years, but still, so they are the idea is that they get used to this pace. So, and for this reason, we use some classical mathematical tools. So we teach them like serious mathematical courses. And at this part of our curriculum, we can use actually classical mathematical courses. So we teach them rigorous proofs, and we ask them to produce these rigorous proofs. We teach them like algebra, calculus, discrete mathematics, and all this stuff. We try to force them to solve as challenging problems as they can. In terms of engineering, well, we try just to force them to study to study a lot on their own. So sometimes we just give them a problem, and then we say, okay, so there are modern tools that can be used to solve this problem. So like today your goal is to like teach a model to play some game, to implement Tetris, or to solve that particular task. And you can use any tools you want. You are free to ask our professors any questions. You will then see how our professor solves this problem. So they always need to run quickly. They always need to catch up with all this stuff. Not everybody is able to do this till the finish line, but the statistics speaks for itself. So usually when a student graduates from our bachelor program, it is very easy for them to find a good job in various fields, actually. So I mean, we have reasons to believe that this will stay the same, even despite the fact that we are not sure about the world in 4 years.
But but I still want you to be a little bit more specific. Do you have your favorite complex task for the students? Like, what if you would choose if you are to choose one thing to work on with them, what would you choose?
So for the last for the last 3 years, somehow I'm still interested in working on this competition on Boolean circuit synthesis with students. I mean, it's not because I believe that this is too important for them, and this is not like an obligatory class for everybody. I just invite everyone who is interested to work on this competition because among our students there are many Olympiad winners, so they are definitely motivated by participating in competitions on the one hand. On the other hand, this is a different type of competition, so we optimize these objects called Boolean circuits for something like 4 months. And you can apply many techniques here, like discrete mathematics, combinatorial optimization, machine learning. We still haven't figured out how we can use the latest advancements of artificial intelligence to get better circuits, but we are trying. I mean, through these projects together with students, we actually investigate a lot, and this is just fun for me. Also, after the first competition, it was in 2024, and we actually got the first place in it, so which we used to publish 2 scientific papers together with students, which is, I mean, good enough for their future studies and their future careers. But this happened more or less accidentally. I wouldn't say that this is the favorite project of mine. We found this competition and we decided to participate in it. So next year probably we will participate in some other competition. So we'll see. So going back to your question once again, I don't think that I know something like the project that every computer science student should at some point try, especially because we also try to somehow like respect the fact that different students are interested in different fields. So those who are interested in like writing code, optimizing code, and also thinking about new algorithms are welcome to participate in a project with me. Some of them are interested in just some software engineering, so it like developing some servers, some games probably. So they work with other professors, which is cool. I mean that they have many possibilities to try different things.
I will just turn a little bit to Igor because I know he's also teaching students. Do you have any favorite task for them in this changing world? Imagine, like I don't have engineering background. My background is from somewhere in between psychology and neuroscience. If you are to give me 1 or 2 problems, maybe each of you, to learn, to go deeper into the field, what would you recommend me to work on?
I was teaching one course on computer vision in Neapolis University, and I don't have like one specific problem because it was like introductory course to computer vision, what I liked about the students in Neapolis University is that I constantly increased the level of difficulty, of complexity of my tasks. And I was trying to find this level when they fail. And every time there was like one or two students that passed this. Maybe it's to the question, what AI gives us. So right now, it's even easier to take a task of any complexity and at least to start iterating with it and have some first steps and also to work with someone with AI. But for the specific problem, I don't have one, I suppose. I like the problem of implementing a game of life. You can do many things with game of life, but the interesting thing with game of life is you can, if you want, you can train the neural network to predict the next step. And this is how you can use the network to find some specific states, like the circle loops for like 3 or more steps, actually 2 or more steps, by applying the methods that usually people in computer vision do for noise reduction or creating images, like generating images. So you can do this to find specific states in game of life. But we didn't do this in that course, maybe in the next one.
Yeah, it is indeed exciting that this classical just problem. I mean, I guess there are textbooks which are probably 30 or 40 years old that also discuss the game of life, and they suggest it as a nice programming project. And so Igor just mentioned that this is also indeed a nice project with a modern, with the possibilities of applying some modern tools for this. And also I just probably a week ago, I saw a professor from Carnegie Mellon who is teaching a course on which is called Programmers for Lovers. His name is Philippe Campo, and one of his projects actually is a game of life indeed, and he is still using this nice game as one of the projects in his course.
That's a good metaphor. That game of life is still important to learn how to orient in these changing and complex systems. Okay, another thing you've mentioned, which is I think really interesting, is this world of competitions, mathematics Olympiads, for example, which are now tackled by at least this year, and was it last year also, only 1 year, by AI. I mean, IMO gold medal for LLM. Can you comment on that? First of all, were you convinced that this is a real accomplishment of LLM, or is it just some engineering brute force approach? And how does it change this world of competitive mathematics?
Yeah,
if it does.
I must admit that I don't know exactly whether it changes. So probably I would expect that it changes indeed. So I would say that the current advances of AI actually changes the whole world of mathematics and the way mathematicians are doing their job, and also it seems that it becomes more and more difficult, of course, to find problems for homeworks, for mathematical circles that cannot be easily solved by LLMs, and they are definitely getting better and better. It's amazing actually that LLMs were able to solve mathematical tasks at the level of IMO. So from what I heard from probably the previous year is that they first translated the problems into Lean. So the organizers, or the ones who used LLMs to solve the problems, they formalized them first into Lean, and then LLMs were able to find the solutions in Lean, which were a bit strange on the other hand. On the other hand, Lean is kind of the language of of machines, for example. So machines can find proofs in this language, but from what I saw, the machines are already quite good in producing proofs in human language, so to say. So of course we still see some arguments that are flawed, but I mean they are definitely getting better and better and better. And many mathematicians actually reported already that AI assistants are just good collaborators. And from some famous mathematicians, I saw that probably several years ago, LLMs were on the level of I don't know, good bachelor student, and now they are on the level of good PhD student, for example. So there is definitely progress, and if this continues, I'm a bit frightened and nervous. On the one hand, on the other hand, I don't have a single paper with some mathematical theorem which was proved with the help of LLMs, for example. So
yeah, but how does it work? I mean, what is the difference between Olympiad's medals, IMO, and real mathematical research? So how do you use LLMs in research where it can really help you, where it doesn't? So how is this world of research is changing?
I mean, it is still unclear to me where is exactly the boundary where LLMs can help you and where they can't. From what I've heard from other people, for example, how they use it, sometimes you just have a discussion with LLM, with a chatbot. It is specifically good when you need to apply some known method to your new problem and just to check, so it can verify quickly whether this particular method gives something for your new problem. You can also ask it to suggest some new ideas. Sometimes, as many of us, I think, have seen, when you ask it to produce a proof of some mathematical statement, it can be the case that everything looks good, but then some particular small transition, which actually look easy, is just flawed. And then you need to redo everything. And there are successful cases of fixing this as follows. So you first ask LLMs to prove something, and then you say, and then you ask LLMs to formalize this immediately in Lean. And then if it fails to formalize this, then you ask it to start producing proofs and formalizing it in Lean, while the formalization and its proof in Lean is successful. I haven't tried this one yet, but will probably do. So I'm not familiar with Lean, so I still need to learn it. It seems that Lean and formal verification also becomes more and more important in view of all this advancement of AI, and probably it will also shape the way mathematicians are doing their jobs.
I had a follow-up question about formal verification and actually formal machine proving of theorems and everything, because it's not a new field, I suspect, and right. People were doing formal, like trying to formally prove some theorems long ago. And I have this analogy. I'm not sure, like, is it relevant or not? So, for example, in chess, in the game of chess, there was like a long-going history of beating humans, and it succeeded long time ago. And we had like fish and also AlphaGo. And if you ask any LLM to play chess, it will play on very intermediate level, despite the fact that it was trained probably on the old chess books and it had the access to all the chess plays in the history. But still, it's not that bad. It's not that good. Specific engine is much better, and I suspect why in the question of proving the theorem, the baseline is not only human, but also the machine. So are LLMs like much better than machines, or the like classical machines, I would say?
I must admit that I just don't know. I've never seen such comparisons. Once again, for the third time, this comparison with chess also frightens me a bit, because I mean, machines were able to beat humans in playing chess. I mean, and there are definitely some similarities with between playing chess and, like proving theorems, or finding theorems of mathematical statements. So what prevents machines to become better than all the humans in proving theorems in the nearest future? I don't know. So I hope there are some limitations. Okay, but probably there are not. There aren't. But okay,
people are still playing chess. That's no. I mean, you're saying that this is frightening, but actually, your comment for me sounds like a bit of optimism. People are still playing chess; they still enjoy it. And
right.
well, I wouldn't say that a lot of mathematicians were starting trying to prove mathematical theories to do something really practical and pragmatical. I mean, if people are just like solving these puzzles and it has very unexpected results, but as they are still chess players and this is a huge field, mathematics can still be the same. I mean, can you comment on that?
I hope so. On the other hand, so there are different, definitely some similarities, but there are also other like pragmatic aspects. Because I mean, okay, so people are still playing chess, but many of them, I guess, play chess for fun. So there are not probably so many professional chess players. But when I speak about mathematicians, I mostly speak about professional mathematicians who need to be hired, for example, and who need to feed their families. And if machines start to prove theorems faster and better than humans and than mathematicians, then probably there will be some issues with job positions for mathematicians. So your argument is that these mathematicians can still prove their favorite theorems, which is good enough, right? But what about feeding their families? Okay, so more seriously, probably I actually don't expect this to happen in the nearest future. On the one hand, on the other hand, I mean, I was not expecting machines to start writing code so good, so that like many professional software engineers start reporting that they like stopped completely to write any code by hand. So they only do this with AI agents. I mean, I was not expecting this, and for this reason, probably it's not that important that I'm not expecting machines to replace human in proving theorems. So what else remains? I mean, we'll see. We'll see what happens in a couple of years.
You've told before that you are interested in trying to build some software for agents to be able to prove something. What's the reason, your reasoning behind that? And in your opinion, how should it work? And so probably this is the point where AI of today meets mathematics. What is interesting for you to do in this field?
Yeah, so what I mentioned actually is I guess is probably less ambitious, so to say, than just AI agents like finding some new algorithms or something. I just wanted to check whether AI agents would be able to implement some programs, some specific programs that probably not many people are interested in, but so I'm still working on this like circuit synthesis problem, which is an extremely difficult problem in practice. I mean, even with the advancement of all AI tools and different software for combinatorial optimization, we still have no idea how to solve it in some reasonable time in practice. So we are trying to solve it at least in some special cases. On the one hand, on the other hand, some technologies change over time, and by technologies I mean technologies for in chip design, so to say. So Boolean circuits are the model for microprocessors and chips, and I was mainly focused on some specific technology, and I have a lot of software implemented for optimizing this technology, so to say. In order to switch to another technology, I need to rewrite all my software from scratch, because it is not so easy to adjust it. So my current plan is, when I have enough free time, I will just try to ask AI agents to write all this code for me, by probably pointing them to some of my code and to the code of other people, and also to some scientific publications on this. So let me brag a little bit at this point. I actually, several years ago, something like 15 years ago, I implemented, together with students, we implemented a program for circuit synthesis, which is based on SAT solvers. And we were able to find some new circuits with this software, and then it was re-implemented by Don Knuth. And I even got a few emails by him, by this living legend himself. And then after a few exchanges, he also sent me the current part of the art of computer programming that he was working on. I was proofreading, and I found a little typo in it, just a small actually inconsistency, and he in return he sent me a check signed by him, which I can. So this is a check for $2.56, which I can which I can cash if I want, but of course I'm not going to definitely. So I just keep it in my
Is it
apartment.
signed by him?
Yeah, by him, and also the envelope was also signed. Okay, so the envelope was signed by his secretary, but inside there was a piece of paper with my address written by his hand. Yeah, I also met him once at one of the conferences. Yeah, and this was amazing. Yeah.
I think with his handwriting, it's definitely worth more than $2.5.
Oh yeah, definitely, definitely.
So coming, well, this is great, just a great story about this tool you've built with the students. Are there any other directions that you maybe not pursuing right now, but you think might be still interesting, or maybe becoming interesting with all these fast changes in the field? So what is also promising in your opinion, of course, in the world of complexity?
In the world of complexity,
no, maybe wider than that. Maybe wider than that.
Yeah, so this is a challenging question. I'm not sure. So what I basically, with the help of, when we now have such powerful like assistants as the state of the art AI assistants, I'm just trying to apply them to all the problems I was thinking of, but it's difficult for me right now to think of some new branch that I was not thinking about before, where AI assistants can help. So my guess is that I was still using them for some subfields of complexity theory, where I treat myself as an expert. Or so we recently, together with my colleagues and with some students, we started to to study distributed algorithms, but I think not because of AI, but just because we decided that this is like an interesting and fascinating area on the one hand. On the other hand, we've learned that it has some connections to circuit complexity, which basically means that we can probably contribute somehow to this field because we know a lot about circuit complexity. So we'll see once again.
Great, thank you. Let's switch a little bit from this part. Another thing I really wanted to ask you about is your experience with large scale, really large scale education. To our listeners, Alexander is the lecturer on maybe the biggest course on mathematics on Coursera or something like it. At least it's huge, with a huge number of listeners throughout many years. How is it to feel that you've affected so many people? Do you have any personal stories that came through this huge thing, teaching so many people online?
No, I don't think that I have some personal stories. So it all started. Actually, I started producing online courses in Russian. Actually, back when I stayed in St. Petersburg. Even some of these courses are actually quite popular in Russia, and at some point, I mean, in different places, people actually told me that they watched my courses and they learned algorithms from them. Even at JetBrains, I actually met some people who told me, okay, you are the guy who taught the algorithms course on STAPIC. The reason for this is that algorithms are still one of the subjects that are discussed at interviews in tech companies. We'll see, by the way, whether it will change or not. So, like, algorithmic problems has been used for decades as a test for whether a person is able to solve some new problems just online, in a sense. Probably for these reasons, algorithms are still so important and so popular. Right. Then I produced these courses for Coursera, and it was. It changed my way of thinking about online education, because in my previous experience with offline teaching, I was always working with people with some mathematical background, actually, and with some experience of mathematical proofs and so on. And then after producing these courses, I spent something like probably one or 2 years by answering most of the questions at the forums at Coursera, which actually allowed me to learn exactly the places where it is difficult for many learners to understand what is going on, or to wrap up their head about it. I also, it was surprising for me, but could you probably guess what, we implemented this auto-grading system for our students so that they can submit their solutions in virtually every possible programming language. Well, probably not every possible programming language, but there were 15 programming languages available for submitting their solutions. And the goal is, as usual, so you have some computational problem, and the question is to implement a solution that works fast enough, even on large data sets. And just to give them this feeling of being fast for a solution, we usually provided them with some starter code, which implements some naive algorithm, so that if you run it on your laptop, for example, or in our grader on some large data set, it starts working for 1 minute, for example, or more than 1 minute. And in our grading system, we ask them to implement a solution which works under 1 second. So our first version of the grader actually contained something like 10 programming languages, and in a few months people started to complain that one particular language is missing. So could you guess what was this language? Which is probably one of the most popular programming languages that is used by our learners at the algorithms course. No, C was in the list, and it was not so popular.
I have two options, Python and Kotlin. I don't know which one.
Yeah, definitely we had Python and Kotlin, so students were definitely able. But one language was missing because we thought that this is not the language for implementing algorithms, but students complained a lot.
Pascal,
MATLAB.
MATLAB, yeah.
No, it was actually JavaScript. So JavaScript is probably not the right language, so to say, to implement algorithms, right? So this is just, I mean, this is probably intended for web applications, but it turned out that this is like the language of choice for many software engineers, and they were sometimes it is not that convenient in JavaScript to work with large data sets, but still, so they wanted to. I mean, before producing this course, I haven't even thought about it, that we need to add support for JavaScript, but then I learned that it is important for so many people. I guess for many front-end engineers, and we added the support for this language, and people, I guess, were happy.
You were saying that, first, personal story. I learned how to code quite late when I was second year student, I believe. So I was starting as a psychologist, never thought I was going to code anything. And for me, understanding why do you need algorithms was a tectonic shift. It was not from my first attempt. Like I tried several times to learn some language, and I was told that, well, here's syntaxes, then you can have a cycle, you can have loop, and then some very, very complicated task, which I had no idea how is connected to these loops and cycles. And it was some time and maybe some specific, for me, it was data science problems that I came across that really showed me what is the power of algorithm. And it was really a tectonic shift. After a while, I really realized that the way you can think, if you can think about something algorithmically, it's really a way to see any problem from a very, very different perspective, and, well, really, really important. You were saying that you've seen, so I probably was, I haven't at that time seen your course. I've seen several lectures later, just because I've heard that this is a brilliant course. But you were saying that you learned a lot on how people without deep mathematical engineering experience learn stuff and questions they were asking. What were those, and what kind of skills are those that can be trained with this algorithmic thinking? So tying back to our complex problems that you still need to teach how to approach your students. What is the skill of solving problems? In my opinion, definitely tied to algorithmic thinking, is there? What kind of things people struggle with? How did you approach talking about this? Can you tell a little bit about it?
Yes. So one of the things that became quickly clear to me, I mean, I would even say one of my mistakes while recording the first version of the course on algorithms was that it is probably not a good idea to analyze the algorithm, the correctness, for example, of algorithm, or the running time of this algorithm using some mathematical machinery, for example, mathematical induction. So it was though I was taught mathematical induction in high school, somehow I lived in a world, I lived under an impression that everybody is taught mathematical induction at high school, which is, I mean, it is obviously not the case, but somehow it was not obvious for me. I don't know, 10 years ago, for example. So after realizing that people struggle actually with when you just say, okay, let's prove this fact by mathematical induction, and this is like a particular place where there is a learning breakdown for some of our students. So I tried to redo some of this part, because in some cases it is actually possible to avoid using these fancy words and prove it somehow probably a little bit less formally, but more intuitively for them. And sometimes it is of course more important. I was thinking a lot about how can I explain algorithms, not just to explain them, but help everybody to arrive to these algorithms, to show the way one could potentially invent such an idea. And for that, we actually also at some point implemented some puzzles. I mean, sometimes you can play with, I don't know, with a 7 years old, you can play some games, like if I have a number from 1 to 100 in mind, and you asking me questions whether it is smaller than something or faster or larger, then after a couple of attempts, they realize, and it probably makes sense to cut the current range in halves and to proceed. And this way, if you start explaining, say, binary search like this, and probably you help the learners to understand the whole method of binary search better than if you just take it out of your pocket and show it to them. So speaking of algorithmic thinking, I do believe that it is important, and also there is this. Since I've been working in algorithms and teaching algorithms and reading different books and different forums, for many times in my life, I actually saw discussions in somewhere in the internet of the following form: when there is some software engineer who works for some top tech company, like I don't know, like JetBrains or like Google or Meta. So he or she can claim something like that he was studying algorithms at the university, and then this person has been working for 20 years as a successful software engineer, and hasn't used algorithms for the last 20 years or so, for example, which can potentially be true on the one hand. On the other hand, in fact, indeed, as you mentioned, when you study algorithms, you actually, what is probably more important than learning some specific algorithms is to learn this algorithmic thinking. So you know how to decompose a problem into chunks, which can help you even in real life, and actually in probably even in prompting LLMs, for example. So instead of asking LLMs or agents to solve a huge problem, you decompose it in your head into smaller ones, and then start prompting piece by piece, so to say. And also, if you just study algorithms in your course, then and you optimize your code, you try to design better algorithms, then you actually know, well, you get some practice about code. So you know that there are cases where there are two nested loops, and you can replace them with just one loop. So 2 nested loops are not needed because you are solving some simple task. So and actually, those software engineers who actually claim that they never use algorithms in their life, so they're probably not telling the whole truth. I believe that sometimes they're using algorithms without actually realizing this.
I wanted to share one personal story. We can cut it out afterwards if it's not relevant. It was one time in my 14 years in tech when I needed an algorithm to invent, and the task was I was working on something like Google Maps, and I needed to understand which countries are presented in the user screen. So the user screen is some rectangle, and countries are non-convex polygons. There are many, like one country can be many polygons. And I have all these polygons as like JSONs or something. And I needed like some quick way to understand like how they intersect, like which countries are in the screen. So I think for a day, I like wrote some numbers on the board. And then I came to non-trivial solution to ask on our internal forum how to do that. And after 10 minutes, someone responded to me that, okay, we have a function for that actually in that library, so you should use it. This was the only time that I needed algorithms, like like explicit algorithms, not internal algorithms. Back to you, Ilya.
No, it's a great story. I mean, it's really I agree with that thinking about the world algorithmically is changing. With your story, Igor, I believe the thing is that it's trivial for people in computer science and probably trivial for a lot of people listening to the podcast, but it was not always trivial that you can approach the problem like that. And this is, I believe, important. And this is a very interesting and I think complicated question, how to teach stuff like that when so many problems can be solved zero shot with LLMs, how to preserve this view of problems that you can decompose into some smaller problems. And basically, like, I wouldn't say that scientific method and algorithmic thinking are the same, but they share a lot together. I would argue more. I would argue that sometimes scientific method can contradict with algorithmic thinking. And personally, mathematical induction and real world induction, sometimes living in a world of mathematical induction and algorithms gives you very, very misleading, at least in my point of view, understanding of the more complex biological world, but still the ability to do that is important.
Mm-hmm. Right.
But you have a great story about, maybe not algorithms per se, but applying your knowledge from complex engineering mathematical world to some other field. Can you share this story? If someone looks at your Google Scholar, they'll see that your the most cited paper is in the field of bioinformatics. How did it happen? What did you learn in the process? What's the paper about? Can you tell us what you've done there?
Yeah, so let me start by saying that for that paper, so this is indeed a highly unusual paper on my publication list. It is about a genome assembler called SPAdes, which we implemented back in St. Petersburg under supervision of Pavel Pevsner. So he is like a world famous bioinformatician applying like algorithmic methods in computational biology, and he founded a lab in bioinformatics at some point. And I was back then I was working on some fundamental stuff in theoretical computer science, and I was actually tired at this point on working on all this. I was trying to prove lower bounds, and this is sometimes it is just depressing, so to say, because you are trying to prove something, and I fail, and I fail, and I fail, and we still lack mathematical methods for proving such lower bounds. So I decided that I need probably to shift from this fundamental stuff to more applied stuff, where we implement some code, and actually it looked as a very promising field for me, because in bioinformatics, you, on the one hand, you definitely need to implement various algorithms. The data sets are huge, so you for sure need algorithms that are extremely efficient. And there is a third reason, is that potentially your research can have impact for biologists, for medicine, which was nice. And we were working on this assembler. Then we implemented it. Let me also emphasize that I was not the top contributor to this piece of software. And then I actually switched back from bioinformatics, because I actually realized that through the problems in bioinformatics are very interesting, and the team was really cool. There were many people from St. Petersburg who are experts in algorithms, and but still somehow I was in my free time I was thinking about complexity theory and fundamental stuff. And at some point, I actually realized that the truth is that I don't care whether the mathematical questions that I think about all the time, they have any applications in real life or not. So somehow it turns out that these are the most interesting questions for me right now. And then I decided, okay, probably it was a mistake for me to think that I really need to have some impact of my research to real life. Okay, so there are some fundamental questions, and I just want to solve them, and this is probably it. So I discussed this with Pavel and switched back to the fundamental stuff. And fortunately enough, we are still good colleagues with Pavel, and we published a book on algorithms, and we created those online courses on algorithms. Pavel is still doing bioinformatics, of course, is still publishing books, and I'm happy to help him in when he needs something from me. And I visited him two times in San Diego, so we're still good friends. But the paper became so popular, in particular because many people who work in genomics use it as a tool, and each time they use it, they just cite it, and it never happens in mathematics, of course. So there are 50 papers in mathematics or in theoretical computer science, and one paper in bioinformatics. And that one paper in bioinformatics accumulated something like 30 times more citations than all the other 50 papers altogether, which is amazing. But even compare it to other applied papers, so to say, this paper is quite successful. It's not that all applied papers have so many citations. This is fascinating. This just learned me that taught me that I'm sorry that in applied sciences such situations happen. I'm not even sure that there is a paper in pure mathematics that has so many citations. Probably even for classical papers, the number of citations is smaller.
Yeah, I believe this is just yet another example of how hard it is to objectively quantify the impact of scientific worker, because the fields are so different. Bioinformatics is very centralized. There are a huge amount of people, huge amount of works with the same methods, and I doubt that there are many fields that work like that. I have a friend, Alexander, both of you actually know him, who has some impact, who was working in CERN during one of the most important papers on Higgs boson, and he's not doing science for 20 years from that time, and still accumulating more and more citations for that. I mean, there are just different fields of science that works differently, and
Right.
that's okay, but that just shows that these things are hard to objectively assess in any way.
Right, right.
But at the same time, you've said that you are not. Well, first of all, thank you for your honesty. I think there is some well, at least I feel it, some pressure on trying to make your research useful for someone. And in mathematics, it's not like that. And there's a lot of people in mathematics who are doing stuff that are not easily tied with the reality. But at the same time, there are so many examples when things that were not at all planned to be practical appeared to solve so many practical problems. I don't know, in 50 years from that. Talking about big topics that really motivates you in science. So are there any big, like, imagine you are on sabbatical and you have like 4 months after sabbatical started, you are already relaxed. You've visited Bali, you've visited whatever your dream is, and you are thinking of a new problem to solve. Are there any big problems that you've always thought of as something you would try to approach one day?
So tell me, so that I can just complete the picture. Am I visiting Bali together with my kids, for example, or am I visiting?
Sure. Well, depends on you.
Oh, so I'm free to bring them, and I'm free not to bring them. Okay.
Yes.
Right. So let me, by the way, get back to what you previously mentioned, that there is some pressure to kind of explain whether my research has some impact on real life or not. So I would say that it is probably not a pressure, but I just returned back from the conference where on my badge it was saying JetBrains, and just several people asked me why JetBrains is interested in hiring a person who is doing complexity theory, actually. So I was explaining it several times, so I decided that it probably makes sense to explain it here also. So JetBrains at the same time as a company haven't asked me at any point to produce something out of my research. So going back to your last question, where I'm visiting Bali and trying to solve some problem with the help of AI assistants, probably with the most modern and the most powerful. So I do have some favorite problems. I would be happy, of course, to prove. My dream result would be to prove that there is some natural problem. For example, I don't know, coloring a graph. Or I don't know, finding all pairs shortest path in graphs in a graph, or I don't know, subset sum or something. It would be just nice to have a mathematical proof that some of these problems cannot be solved in linear time, for example, on a computer. I mean, we don't expect them to be solvable in linear time. At the same time, for some reason, we just don't have mathematical methods to exclude such a possibility. It is too difficult to reason in terms of all algorithms, and we somehow need to show that all fast algorithms, none of the fast algorithms actually solve these problems. I mean, I wouldn't say that this is a very ambitious goal. I mean, an ambitious goal is actually the very ambitious, or the most ambitious goal in our field would be to prove that P is not equal to NP. And for this, one needs to actually show that coloring cannot be solved in polynomial time, for example, that it cannot be solved in time n squared and cube and n to the any like constant power. So what I mentioned previously is much less ambitious goal, just to prove that some natural problem cannot be solved in linear time. So this is, as I mentioned, this is a dream result, but at the same time, I must admit that I don't have many like promising ideas in this direction. So we're exploring different fields, different directions for proving results like this. Sometimes, because we cannot prove this in full generality, sometimes we just consider some restricted models of computations. So we say, so assume that that we are considering not just like arbitrary algorithm, but an algorithm that cannot. So, for example, there is a result like this, that if you need to compare and if you need to sort n elements, or put it otherwise, you have n stones or n balls that looks identical but have different weights, and you have this pen balance where you can take two balls and check which one is heavier. Then in this case, we know that the number of weighings on this pen balance should be at least n log n, which is like more than linear. But in this case, we are talking about this very restricted, so to say, type of algorithm where the only thing that you can do is to compare two objects. In general, of course, we can do much more. So if our objects are integers, and we need to sort them on our computer, then you can, of course, do many other things with integers. You can do some arithmetic with them. You can use them as indices and so on. So we try to approach this problem from different angles. On the one hand, try to prove this in full generality. Okay, we cannot currently, so we consider some other problems. We consider some other computational models. Sometimes we even try to do something in practice, like synthesizing like good algorithms for small input sizes. This is also an open problem in a sense. So I work on all these branches. It seems that if I had just 4 months in a row without any commitments and without any meetings, without teaching and stuff, I would still continue working on all these problems. Probably sometimes when I'm too tired thinking of some of these problems, I still want to somehow contribute to the world, I switch to writing books. And even when I write something which is well known, I still try to. It's still somehow I still enjoy thinking about better ways of explaining, for example, algorithms, and producing some pictures, or in recent years some animations, and we'll see. But yeah, by the way, this is I really enjoyed in the last few years that it became too easy to produce animations in 3 blue 1 brown style. It is a Python library that allows you to do this, and of course nowadays you can just produce such an animation with a single prompt mostly, or probably with prompting and then adjusting this video. So it produces you a Python code, you compile it, and it gives you just a nice animation. And sometimes a picture is worth 1,000 words sometimes, but animations for algorithms work even better sometimes. And not just for algorithms, for mathematics it is also the case.
So you're more of a geometric mathematician rather than algebraic?
Oh yeah, probably. I like pictures, and probably not all people actually think in terms of pictures indeed, but yeah.
Yeah, personally, I'm a huge fan. Yeah, sorry.
Yeah. So I just wanted to add that with all AI assistants nowadays, you can actually explain them when you ask them for some explanation or clarification, that you are this like visual type of person, for example, or algebraics, so to say, type of person. You prefer to start with examples or with pictures, or vice versa. You first need to see an argument and only then the examples and so on. So this is just great that it became so easy to have personalized assistants.
I had a question, but it's a long one. So I will start, and then there will be a question. So when I learned machine learning, like several years ago, there was one example that I think was very impactful to understand how ML works. This example is the difference between interpolation and extrapolation. For example, if you train the neural network to interpolate between dots that in the shape of sine wave, then it will be very good in interpolating. But as soon as you ask what is left or right to the sine wave, it will draw some madness. And this is how I thought about machine learning through the years, because when you ask the model to classify or to regress something within the scope that it was trained on, it produces you some reasonable result. If you ask something extra, it will produce something unexpected. And I think this is some kind of connected to how LLMs works, because some people argue that LLM cannot produce you entirely novel idea, and this means how it can invent something new. Of course, you can invent something new by applying existing methods to another existing problems, and maybe carefully grinding through these different sets of applications, you can find something new. And the first question is what do you think of maybe complexity theory or mathematics at whole? Where the most of, not the papers, but real inventions come from? Are they coming from epiphany, something very new, nobody has thought about this before, I don't know, maybe you need mushrooms together, or it's coming from applying existing thing, but because no one did it before, someone did it first? And also the thing that is connected to it is humor, because since the AI has happened, LM were created, stand-up comics and real people asked models to produce jokes, and usually models are very bad at it. So I actually right now asked ChatGPT to make a joke about computation complexity and AI, and I will read it to you, so you can rank whether it's a good joke or not. A researcher asked an AI, "Can you prove that P equals NP?" AI replied, "Of course, I just need an explanational time to explain it." And it's not the end of the joke. The researcher said, "That's not very helpful." AI answered, "Hey, if you wanted polynomial time answers, you shouldn't have trained me on internet comments." So it's funny, but I don't know, not that hilarious as I wanted.
Right.
So new inventions, or maybe the way how you will spend your 4 months on Bali. Will you try gradually one by one the existing method, or will you try to enlighten yourself and try to think out of scope?
Yeah, so this is a challenging question, and in terms of the new results, so in complexity theory, as I believe in, as also in mathematics, there are of course many results of the form where you apply some known technique to some new problem or some old problem. And I mean, it sounds simple, but of course, when you're working on some particular branch of mathematics, it could be still extremely challenging, and you still need to work out the details and so on. And what is probably more rare is when you connect some to like results in the same field, for example, in complexity theory, or even when you connect some two fields that at the first glance seems to be not connected at all, and then you get some new result. But I actually believe that LLMs can do this, and even so, on the one hand, as I mentioned, I hope that there will be work for mathematicians, and there will be things where mathematicians are still better than LLMs. But from what you, Igor, mentioned before, that LLMs are good on the problems where they were kind of trained, so to say, to solve, I actually saw several indicators that they are good not only on the problems which are like present on the internet, for example. So people who are into Olympiad math, they constantly try LLMs on new problems where, probably the authors who know the solutions post the problems, and LLMs are able to produce solutions to these problems. And definitely they haven't seen the answers anywhere in the internet. I particularly enjoy the results that connect to far away results or to far away subfields of mathematics on the one hand. On the other hand, for me in particular, it is particularly difficult to find such connections. I would be happy to, and at some point I tried. I had some intuition that probably I need to bring the machinery from some other field to solve my current problem at hand, but it all didn't work out, unfortunately. There are some really nice stories in mathematics. For example, the way they solved they proved the last Fermat theorem. So it took something like 3.5 centuries to prove it, and for that the mathematicians actually had to develop mathematics and to actually to construct some bridges between different areas of mathematics. And this is just a great and fascinating story. And I would be just happy to be part of some similar, but probably much less ambitious story. But currently, I think I'm the way of researcher who kind of tries to be in a small field, in a small field of something, and just to dig as deep as I can. So I'm not the way of a research. So there is, I guess there is this classification of researchers called birds who actually fly among all areas of research and observe everything, and they can find connections between different lands, different areas. And there are researchers called frogs who actually stay in some small and tiny area and try to dig. Okay, so this is probably frogs don't dig, but you definitely get the idea. So, and it seems that I'm definitely the second guy of the second type of a researcher, which is okay. So I would, when I'm on Bali on my 4-month like vacation together with my wife, beloved wife, of course, and my 2 kids, and I'm trying to prove new theorems, I would probably continue digging, because this is how I know how to get new results, and I would continue be amazed by results of some other researchers who know how to build bridges between different areas, right?
Well, it's important to have researchers of all types. I mean, we don't know what part of our research will be this important part of this bridge. So their unexpected stuff end up being really important brick. So I think that we might be coming to the end of our conversation, and I would like to ask you just a couple of, if you don't mind, Igor.
I wanted just to add to this idea of birds and frogs that, in my opinion, LLMs helps a lot to like gather this very scattered information about different fields that happening. Because I thought, like, I'm not a professional scientist. I don't know, like, how. I have very little information about how real science works, but I thought that one of the main problems is that we got so deep into scattered and different problems, that people do not know what's happening like outside. And now we have a tool to like combine all these things, like to say like, okay, I'm dealing with some problem. Is there anyone outside who has a paper on some similar problem? And before, you will need like very much hard work to find something, and now you can just ask. Maybe it's harder than this, I don't know, like but it will be easier for sure to have a tool that can search throughout all the publications, throughout all the human knowledge on the modern science, on the modern applications, and to do it in a smart way. So I feel that it's very optimistic. We have optimistic future in science because of this, because like still we need people who dig inside, but we will have more AI birds scientists, I suppose.
I believe it's true. I believe that it's becoming much and much easier to start doing something in new field, and for people who are interested in have this high level understanding. Of course, right now you cannot rely 100% on the tools, on AI tools, but still it's much easier to go from one field to another, to try this, try that, to understand how to ask questions. So yeah, it is a good tool to start new stuff already. I agree. Okay, so then I think I have just a couple of questions. And the first one would be, what was the biggest thing that in the field, this field between research mathematics and AI, that surprised you the most last year? And are there anything you wait for the next year?
Yeah, I guess what surprised me and still surprises me is the way everything changes. So it's difficult for me to emphasize something in particular. So there is this general phenomenon that everything changes so quickly. I mean, especially the world of software engineering. Probably it's not so true about the world of mathematics, but it also definitely changes. I must admit that I don't know what to expect from the next year. This is extremely interesting. I don't even know whether I would like the pace of this development to be the same, or I would like it to be lower, or I would like it to be higher. I mean, it would just be really interesting to see what happens if it becomes even higher. But once again, I guess I'm repeating this for the fourth time in this conversation, I'm a little bit frightened by all this stuff. I mean, I'm mostly amazed with all this advancement, but at the same time, it's just so there are so many possibilities for this development, and yeah. You see, we definitely live in some fascinating times.
True that. And my last question would be like connected to that. So imagine your bachelor students, one of them, great mathematician, you see that he's like really loved mathematics, and he's thinking about starting a PhD career in computational science, in software engineering or computational science, but with this flavor of mathematics. What would you tell him or her? What would be your advice for newcomers?
Yeah, so for newcomers, I would say, so in most cases when such a person, when such a student like comes to you, so they already know something about like complexity theory, for example. They don't start working on complexity theory just the very first day of the PhD studies, and I would say that only do PhD studies in computer science if you enjoy this, because if you don't enjoy this, there are probably other things that you can do without enjoying them, and at the same time you will be getting paid, for example. On the other hand, if you enjoy doing research in complexity theory, then definitely do this, because if you are trying to optimize something, why not optimizing the level of enjoyment? And it's definitely not the case that everybody who works in computer science and in mathematics are motivated by the same questions that I'm motivated, and it happens. Finding the right research area is sometimes challenging. So for me, it somehow worked like at some point I found myself in a situation that when for example, when I worked in bioinformatics lab, in Pavel's bioinformatics lab, still when I was driving, for example, from the lab to my apartment, I was thinking in my head about some of the problems from complexity theory. Or when I was taking a bath, I was also trying to solve some of these problems. So when you found such a problem that kind of doesn't get out of your hands, this is probably of your head, this is probably the right problem. It's not always the case that you get such a field of research from the first try, but I guess if you have such a field, then you are lucky enough, and if you can find a place where you can work with some interesting people on a particular subject that you like, and you are surrounded by people that you like. So and when saying this, I mean just not probably complexity theory, but any research area, then this is just great. And once again, doing PhD, if you are not enjoying this, is probably not a good idea, because there are other cases, and this is it's probably not worth it.
So follow your passion.
All right. Yeah. Indeed. So you you stated the last 2 minutes that I was trying to explain in just a short sentence. Yeah, exactly. Follow your passion. This is what I would say to anybody who asked me about anything.
And play chess if you want it.
Right, and then prove some theorems also if you enjoy this.
Great. Thank you very much for this conversation, and I hope that even though it's really frightening to leave these days, there's still so much stuff happening that is amazing to see. We're living in an amazing time.
Definitely, yeah.
And I have a curse or a wish to Alexander that LLMs will never take away your ability of thinking about complexity theory in the bus or in the car.
Oh yeah. This is great indeed. Yeah, even when
on the Bali beach.
Right.
Great. Thank you for this conversation, Alexander, Igor. Thank you very much. It was a pleasure for me.
Yeah. Thank you.
Bye.
Yeah. Bye. Thank you.